co-authors of this paper have published numerous papers and they obtained over 50 patents in coating-related areas. And as I said, you will tell us about the different methods to measure the volatility of materials.
Sounds okay? Yes. Today I'd like to take about 25 minutes to discuss the relative volatility of materials. And this subject matter is relevant almost exclusively to the efforts to establish a threshold for VOC. But I will try to convince you with this talk that it is, in fact, quite a difficult endeavor to establish a valid and legitimate threshold for VOC, at least in a reasonable range where some molecules will still be designated as zero VOC and some molecules will be VOC. And I will convince you of this by showing you the relationship of vapor pressure to temperature, some examples of vapor pressure lines and curves. I'll discuss relative volatility as a function of temperature, going through some thermal analysis techniques, discuss the use of GC data and retention times to correlate with volatility, the use of chamber tests, and a short digression to checking correlations and then reach some conclusions. The overriding principle today, the overriding point to be discussed here today is the relationship of vapor pressure to temperature, whether that be a pure material, a solution, a mixture, a coating, whatever. We note that vapor pressure increases with temperature in a nonlinear manner. But more importantly, that not all materials trend in the same way. The vapor pressure temperature behavior of not all materials trends in the same way. We'll start just by very quickly reminding ourselves of the simplest model of vapor pressure as a function of temperature. This is really very simple. We view vaporization as an activated process at equilibrium. The equilibrium constant is the activity of the gas divided by the activity of the liquid. This is a pure liquid, so that the activity of the liquid is 1. The activity of the gas is taken as vapor pressure. We just apply the standard thermodynamic treatment that's well known in thermodynamics. And we end up with a two-parameter fit for vapor pressure as a function of temperature. Log P equals A over T plus B. We can associate A with the enthalpy of vaporization, and we can associate B with the entropy of vaporization. We'll just quickly review the methods that we can use to measure vapor pressure. The most accurate means of measuring vapor pressure is to very carefully purify and degas a liquid, a material, place it in a container with a vacuum space above it, and let it attain equilibrium. We then measure the pressure as a function of temperature. If we want a method that's very similar to this, it's almost a direct correlation, we can take the boiling point pressure data from the literature as is collected for vacuum distillations. If there's a sufficient range of this data available, then we can correlate that, the boiling point as the temperature, and the absolute pressure at which the distillation is carried out as the pressure, and we can derive the vapor pressure temperature line this way. We can also try to correlate from thermal measurements, and we can try to correlate from GC retention times. And then there are other indirect correlations that we can use. So very quickly, this is an almost direct correlation of vapor pressure with temperature. These are boiling point and absolute pressure data points from the literature. In the case of a molecule like octyl diethanolamine, there really isn't enough literature available, so a couple of data points were taken in-house from the King of Prussia R&D Center in King of Prussia, Pennsylvania. 4 data points is not a lot, but we can get a good straight line for the vapor pressure temperature relationship for octyl diethanolamine, a molecule that would pretty much be regarded as a non-VOC by most people. I should comment that these are everywhere. These log P versus 1 over T plots are everywhere. There are thousands of these on the internet that you can find. I just pulled one off from the University of Maine. The only thing to keep in mind is that the authors, the preparers of this graph may be using the natural log or the base 10 log. That's about all you have to bear in mind. That's going to impact the magnitude of your constants A and B. Now, one important point to remember, and it's a little bit counterintuitive, is the idea that relative volatility changes with temperature, and relative volatility can actually invert with temperature. Relative volatility is the vapor pressure of one molecule divided by the vapor pressure of another molecule or solution or material at a given temperature. This can be shown graphically with this type of a presentation. Before I show the volatility inversion, I will comment that these straight lines are valid only for a small range of temperatures, somewhere between maybe 50 degrees C and 250 degrees C. In some cases, maybe a little bit more, maybe room temperature all the way to 400 degrees C. At very high temperatures, the molecule is, of course, either approaching critical behavior, which would be completely different from this, or it's being degraded and destroyed. Very low temperatures, the molecule is solidifying. What we see is that when molecules have different entropies and different enthalpies of vaporization, they very often can invert the volatility. So molecule A with a boiling point of 215 degrees centigrade is in fact more volatile at room temperature than molecule B with a normal boiling point of 201 degrees centigrade. This is not at all uncommon. Again, I'll say, you don't need to go far. You can pull these type inversions off the internet. This is just a graphic I lifted out of a textbook. You see the volatility inversion between toluene and water. Now, you can do some math with the straight lines, and you can actually calculate a temperature at which the ratio of the vapor pressure of two molecules has a certain value. It's this very simple expression. And you see that that value is dependent on the difference in the enthalpies of vaporization and the difference in the entropies of vaporization. What you'll note is that within the relevant temperature range, the range where the function is in fact linear, similar molecules tend not to invert. I have the plots here for ethyl formate and butyl formate. But dissimilar molecules will oftentimes invert. This is sort of the classic case of water and methyl isothiocyanate. Methyl isothiocyanate is a common fumigant, space fumigant. And if you can build the mental picture here, the meaning is, you might think to yourself, well, water boils at 100 degrees C and methyl isothiocyanate boils at 120 degrees C. Therefore, I'm going to apply this MITC at 10 degrees C. I know water is not very volatile at 10 degrees C. So I'll have sort of a mental picture as to how much spread I'm going to get for the MITC based on that, when in fact, MITC is more volatile than water at 10 degrees C. Now, of course, bear in mind this is relative volatility. Everything increases in volatility with an increase in temperature. We're talking about the relative volatility of a molecule A compared to B. This is relevant to VOC, of course, and it's relevant to the establishment of the VOC threshold. And this has been recognized previously. There's this 1997 paper where the authors were using a definition of 10 pascals vapor pressure at room temperature as their threshold for VOC or non-VOC. They noted that molecules with boiling points below 170 were all VOCs. Molecules with boiling points above 270 were never VOC. But between 170 and 270 degree normal boiling point, you really couldn't tell. So they established sort of a range of about 100 degrees centigrade of the normal boiling point within which you really had difficulty correlating to other measurements of volatility. And again, you can take this equation for the straight lines and you can calculate this. This would be the volatility divergence. This is a 10% difference in volatility across the range. This is a 30% difference in volatility, meaning one molecule is 30% more volatile at one end of the range and it becomes 30% less volatile at the other end of the range. And the values you see here is a temperature range of about 300 degrees C and about 180 degrees C. And again, this is only important if this inversion is occurring at a relevant temperature. All these lines are not perfectly parallel, and there'll always be an intersection of these two lines. But if the intersection's at 3,000 degrees centigrade, or if the intersection's at minus 100 degrees C, it's irrelevant. It's only when these volatility inversions occur at around room temperature to maybe 200 degrees C that they have an impact on practical VOC definition. It's not hard to measure this. These are derivative weight loss ratios. This is just the time rate of weight loss in a standard TGA experiment, different temperatures. These are pairs of molecules, it's glycerol, TXIB, et cetera. These are various pairs. So these lines represent the weight loss rate of one molecule divided by the other. You can see changes in relative volatility are the rule, not the exception. If there were no changes in relative volatility, you'd have these straight lines going, horizontal lines going across. And anytime these lines cross the one line, you have an actual volatility inversion. So now we can ask ourselves, well, how well does thermal analysis show us these volatility inversions? I'm looking at sort of some theoretical vapor pressure temperature lines that are derived from boiling point data or maybe from actual vapor pressure measurements, and what the thermal measurements show us. We can take TGA measurements, like temperature ramp TGA measurements, or we can take this as an overlay of a DSC for dodecaine, and this is a temperature ramp TGA for butyl diethanolamine. And the output from these methods does give us a temperature that can be identified maybe as a boiling point or a pseudo-boiling point. Well, this is some volatility data from the metalworking field. This is an isothermal TGA method that's run at 81 degrees centigrade, 110 minutes. And we can see that a molecule like dicyclohexylamine is almost, it has a reported boiling point of about 250 degrees C. Now, whether that's been correlated incorrectly or not is another matter. But it has a relatively high boiling point, yet it is completely volatile by this TGA method. And when we look at the volatility of methyl diethanolamine with a similar reported normal boiling point, we see that it's only 16.5% volatile. So certainly huge discrepancies in relative volatility are seen in TGA and DSC methods as well. So then we say, well, what about an indirect correlation of a measure of something with volatility, a GC retention time? Well, correlations of GC retention time with volatility are sometimes okay for a homologous series of molecules, alkanes, esters, all the same type of molecule. And, but the relationship is not very good across different types of molecules. And generally, serious physical chemists use isothermal GC experiments rather than temperature ramps to study this. Now, here's an array. There are three things that influence GC retention time, and this is why I refer to it as an indirect correlation with vapor pressure. The stationary phase polarity has a big impact on the retention time, but there's also an impact of relative volatility, which occurs through the particular temperature ramp chosen, and there's also an important impact of entropy of vaporization. The entropy of vaporization of a molecule into air at atmospheric pressure or close thereof is a lot different from the entropy of vaporization into helium or hydrogen running at slightly elevated pressure. Nitrogen a lot better, so if the helium shortage continues and everybody switches to nitrogen, we may eliminate the issue of entropy of vaporization. But, excuse me, what I just showed there was a bunch of GC retention times that have been measured with the same ramp. Of course, it's easier to see this type of data displayed graphically. And what I'm showing here is that across a wide range of normal boiling points, there's just minimal correlation in the GC retention time with the volatility. Now, there are limits to the ambiguity. If you get to a low enough normal boiling point or a high enough normal boiling point, you can establish with certainty that one is more volatile than the other. But across this, let's use this 100 degrees centigrade range that was established in that 1997 paper. Within that range, you really can't tell. And if anything, GC retention times are more prone to show this problem, not less prone than normal boiling point. And this is just a graphic to show when we consider a volatility inversion of two molecules, A and B, and then consider a GC temperature ramp. This is how the impact of inversion of volatility is expressed. At low temperatures, we see that one molecule may be more volatile than the other, and then at high temperatures, the opposite occurs. So depending on how quickly that ramps up, will have an impact on the retention time. If a ramp stays cool for a long time, it's going to favor the molecule that's more volatile at the lower temperature. If it goes hot quicker, it's going to favor the molecule that's more volatile at the higher temperature. And you do see this. These are normalized retention times for a molecule versus tetradecane with two different temperature ramps. Now, chamber testing has been discussed, and this is the age-old question: what really happens as paint dries? If somebody's ever patient enough to watch the whole thing, maybe we'll know. But at this point, chamber testing tells us what actually does happen. So I disagree a little bit with the idea that there's no correlation between VOC emission and VOC content. If you have an arbitrary definition of VOC and it shows no VOC emission, it may be telling you that your definition is flawed. I do acknowledge they're completely different things. VOC content is a calculated or a measured value from some different set of definitions. But chamber testing does appear to offer a reasonable way to assess what's going on at room temperature, or close there too. This is just the math of a chamber test, which other people have shown in greater detail. Chamber concentrations converted to emission factors, and emission factors then plugged into decay models to predict exposure concentrations in buildings for office workers after a certain length of time or something like that. We have run some comparative chamber test experiments to try to look for VOC. Now I work with Tomeko, the amines company, so most of our work is relevant to amines, and amines are used as neutralizing agents in paints and coatings. But what we did here was to take 3 zero VOC paints based on, a formula based on an acrylic and a formula based on VAE, and we used 2 what were regarded as zero VOC neutralizing agents, and then we used 1 with material which we knew was a VOC, dimethylaminoethanol, a low boiling certain VOC, and we did pick up some micrograms per meter squared per hour of the volatile material. We also picked up a lot of other things that weren't supposed to be there. These were zero VOC formulas, but a lot of stuff that people hadn't anticipated as co-solvents or trace components of their additives were also showing up, in particular benzophenone, which may have been a surface coat to a pigment or something like that. But we do find that the chamber testing is fairly involved, but it does have some value in determining what's actually happening at room temperature. And given that volatility inversions can influence data taken at other temperatures, whether it be GC, thermal, or boiling point derived, we think there is some value in the use of chamber testing. Finally, a quick digression. No matter what you're doing, a good rule is to take the natural log of something and plot it versus 1/T. If you think the measurement that you're making is relevant to vapor pressure, then this plot should be linear. You're not going to know exactly how it relates to vapor pressure unless you can anchor it, but at least you'd say that this is related to vapor pressure. I don't know exactly how, but and I have an example of that quickly. This is, again, some derivative weight loss data. These are just isothermal TGAs where we're measuring the rate of weight loss rather than the amount of weight loss at a given time. And if I take some of this data and I process it, just take the temperature, take the inverse of the temperature, take the weight loss rate, and take the log of that. And now if I plot that, I get more or less straight lines. Again, I see this kink in glycerol, which is a very unusual molecule. Displays very unusual volatility properties as a function of temperature and when mixed with water. So finally, I would say that I would comment that GC retention time, generally, if it's used by physical chemists, they run isothermal experiments. They run a bunch of isothermal experiments, and they only make correlations across similar molecules, like maybe boiling points, predict the boiling point of alkanes, dodecane, tetradecane, hexadecane. They don't usually make correlations from, let's say, alkanes and esters and amines and other polar molecules, because those differences in the entropy of vaporization cause those lines to be different from each other. So then, in conclusion, I would say that vapor pressure increases with temperature. We know that. But the change in vapor pressure with temperature for different classes of compounds trends differently. And volatility assessment as close to the use temperature as is possible is the best option. Now, relative volatility can change with temperature. That's well known. Chemical engineers use that effect all the time in many different separation processes practiced industrially. But it should perhaps be appreciated when one is considering establishing a threshold for VOC. If one's using very high temperature volatility data and correlating that to effects that they assume will be occurring closer to room temperature. And finally, volatility can be assessed in many different ways. This is the best direct vapor pressure measurements. But we can also do correlated estimates of things that are very closely related to the true vapor pressure, or we can do indirect correlations. And chamber testing does seem to offer a great way to check your assumptions in any event. We're going to call VOC emissions and VOC content different things, but still, VOC emissions if you have a formula loaded with VOC, at some point it should show some VOC emissions. And I would sort of also take issue with this idea of VOC content being the loss of VOC over the entire life of the coating, because then after a couple of years we've got to start considering all sorts of other things. The coating oxidizes and then gets clipped off, and the coating will eventually disappear at some point over an entire lifetime, I don't know, 1,000 years. But so in any event, I think chamber testing does offer a useful check on some of the assumptions that have been made. And finally, any data that you collect, you should be able to do a linear plot of natural log of something versus 1 over T. Of course, this is best if you're measuring vapor pressure directly in some manner. And so with that, I will conclude. I guess I'm a little bit early, and take any questions.